Okay, so my session today it's got a kind of complicated title that I've struggled with a bit, but computational graphic structures for geospatial data. And really the point is that a lot of the geospatial data we use can be really compellingly modelled in a different mode in gaming types and in computational graphic structures. And I've learned a lot about this sort of slowly over the years. I've worked with people in the past who knew this back to front, and I've sort of slowly learnt my way around this in R. There's really powerful 3D visualization in R called in the RGL package, and I've been really interested to find what are the pathways we can use to get from geospatial and leverage those tools, because certainly for me it was not obvious, and it took a lot of the time. I just thought it doesn't work at all, but there were a few little tricks that I finally realised that I was missing. So there's a little bit of a setup. So if you're actually doing the workshop, I hope that you can run a few lines of code. It makes sure we have some packages ready and some data downloaded that we'll use. So please just let me know if you have problems with that. It doesn't take too long, but it'd be great if you can try that before the workshop. And I did have to fix a bug in one of my own packages this morning from GitHub. So if you have problems with installing stuff from GitHub, don't worry about that part so much. We'll still discuss the concepts in detail and talk about it. There's really three sections. So here's the getting set up. So there's a link to this book resource in the calendar for the event. Getting set up is really, it's making sure we've got a bunch of packages installed from CRAN. It's written in this slightly abstract way because it won't reinstall stuff if you've already got it. There's a couple of my packages off GitHub to install, and they should go straight forward if all these above do as well. There's a download of an R data session file, just with data objects I use in the session. And there's also an image that I get download. So there's this freely available image of the world. And that gets used as a texture on a surface in part of the workshop. These are a few functions that I use in the book itself, so you probably won't need those, but they're harmless. There's three sections. I'm going to talk about 3D and mesh forms of spatial data. I'm going to talk about and how it really relates to geospatial and some of the concepts I think we need to have. I'm going to talk about the mesh 3D format in RGL, which is a really powerful way of having an object with both its sort of geometry and its topology, its material properties, like its colours and the way it presents when you plot it in a 3D scene. And the different primitive types that are available with that. So there's quads and there's triangles. Lines have to be decomposed to segments, but RGL doesn't really have a formal type for that. So again, that's one of these little obstacles in the way where things don't kind of work out in the obvious way you'd think. And then I've got some techniques for transforming our regular spatial data, so rasters and lines and polygons, and getting them into RGL forms and understanding how that works. And then there'll be sections on just exercises and examples that we can work through together. Some of the key concepts that I gave this talk at Phos4G Oceania last year. It was one of the first times I'd really presented these ideas. Like, they're not like mysterious ideas, but there just really isn't a crossover in our communities, and I'm really hoping to find more people that are interested in exploring this area and understanding how we cross these different types of data. So the key questions are, what are meshes and topology? And I've had a lot of conversations here where topology means a bunch of different things. If you talk to mathematicians, it's quite different. Usually in GIS, we're talking about the old ArcNode topology model in ArcGIS. But here I'm really talking about a broader than that, where the topology of shape is composed of smaller pieces. And so that's really called finite element in other contexts. So lines are decomposed to segments, polygons and surfaces are decomposed to triangles, And if you have volumes, then they're also decomposed to smaller volumes. But there's clear relationships of meshes to raster and vector data, but there's some sort of key concepts to understand, and the different ways we interpret GIS data. What is a mesh? Really, the key thing is that topology is the shape of things and their relationships. And geometry is the where. And really in GIS, we tend to mix those two together. Like, we tend to talk about 2D is X and Y, 3D is X, Y, and Z. But the topology itself is one-dimensional. Like a line segment is one-dimensional topology. And a triangle is two-dimensional topology. So there's kind of two dimensionality concepts that we tend to conflate in GIS, but they're quite separate. And the neat thing about separating topology and geometry is that it can be denser, so you don't have to store every vertex more than once if it's shared across features. And the key is the indexing. This is the thing that links them together. When you go to 3D visualization in R, you absolutely have to do things this way, so it's a key concept. This is as much code as I'll show this morning, but what I'm really doing is showing in R that the geometry, I have 3 points in three-dimensional geometry. So there's an X, Y, and Z value for 3 points. And the topology is of length 2 for each line segment. And what this number is really the index into that array. So the 1 and 2 is the first two rows of this geometry array. And all that really means is that we use the first vertex once and we use the second vertex twice. But this defines the line segments. And if I stored this line, if I stored like a two-part line in a GIS, then I'd really have 4 coordinates. And again, that kind of difference between, there's dimensionality in geometry and dimensionality in topology, and I think it's really valuable to keep those concepts separate. What that means in terms of a 3D plot is that really we have exactly the same data, whether we use that geometry as a line, 2 pairs of line segments, or as a closed triangle. And so, like, when I draw the line segments, I have that topology index, but when I draw the triangles, I just have a slightly different way of indexing how those vertices get joined in the primitives. And that's a very low-level key concept. I sometimes say to people, we do things a bit wrong in geospatial, we miss some opportunities, and really we mix up topology and geometry. Polygons are actually equivalent to lines. Like when you think about meshes and topology, polygons are really just rings, and it's kind of this shortcut in planar geometry that's really fast and efficient and has got us a long way, but it doesn't actually extend into higher dimensional forms. And one of the key problems, I think, like 20 or so years of simple features, is that when the standards were defined, this was practically impossible. But there have been algorithms and methods that have come out in the last few years that are more accessible and allow us to do this. There's more than one way to do it, and there's cheaper and more difficult ways to do this. But that on its own is a hard problem. And the other key concept is raster and vector aren't so different when we look at data in this way. Like, it's a kind of unnatural division in GIS to say that raster and vector are completely separate. But when you start looking at meshes and multi-dimensional data, they have commonalities that are really bridge that divide. These are some of the motivations that kind of got me down this path. Tracks and point clouds, like as Anita was explaining before, it doesn't really fit well in a GIS context. And I think this is part of the problem. We should be thinking about tracks as connected meshes more than we do. It's also useful for topology fixes, and I know a lot of the libraries that we use for fixing geometries actually use these techniques under the hood, but we don't have express access to them unless we use very low-level tools. So in the talk, I go into quite a lot of detail about these vector and raster types and how they relate to meshes. But that's enough for now. Thank you.
Questions for Mike to take now? Plenty of time later on.